Okay, if we're doing this right, you should hear me, but I shouldn't hear you, because if I hear you, then I'll hear everything in the background at your house. There should be something on your screens for you to raise your hand. Anybody who wants to try to raise their hand, find the little icon for raising your hand. All right, good. Alexis found it. It's somewhere on the screen. And then I'm going to switch to advanced sharing options. No, what do I want to do? I want to share my notes. Why is my PDF of the notes not? Okay. And now the okay, the thing that shows me the list of you guys is just gone. No, that's not the view I want. Let's see, manage participants. No, I don't want advanced sharing options. I want manage participants. Okay, I want this list. Okay, I see a list of people. Let me join from my other device so I have a backup. I'm going to join as co-host from my other device. Okay, so I see that on the other device. Zoom to. Why is full screen mode not allowed? Okay. Now I'm getting feedback from my tablet, so I'm going to turn down the volume on my tablet. It won't take the call volume all the way down. Disconnect audio. Okay, so now I can't be heard from my tablet. We still have a few minutes left before we start. Then I'm going to go to full screen mode with that. And I have the participant list on the right. I'm in full screen mode. And I think we're recording. We'll see if we are. We'll find out the hard way in a little bit. I can go to my other. All right, I have 3 screens here. Okay, on my other screen, documents, Zoom. Yeah, it looks like Zoom is recording right now. I see the folder where that file is being created. So that's in place. All right, so at this point on the screen in front of me, I have the lecture slides, and I have the participant list, and While we're waiting, I'll wait a few more minutes for a quorum of people to log in. If you look at homework 13, which is moved to the bottom, there should be a place where, okay, let's get this out of the way. I'm going to switch to student view for Blackboard right now so that I see what you're seeing. For assignment 13, adding waves, there should be a place to upload your submission. So if you can, please do it there instead of on the instead of by email. We'll wait a few more minutes. I see 12 people on the meeting, but 2 of them are me. Why 2? I contradict myself because I contain multitudes. All right, we'll wait 1 more minute. These people are showing up now. All right, let's get started. This is an experiment. I've never taken an online class. I've never taught an online class. So we will do what we can. Let me start by saying that there have been a whole lot of rumors going around, a whole lot of contradictory things being said. I know that while the campus is supposed to have a consistent policy, different things are being done in different departments and colleges. All I can say to you is that physics classes are not in general meeting in person, with the exception of labs I'll get to in a minute. I know that in some colleges and departments, they may be saying that you can still come to class, but I'm not doing this in the lecture hall. I'm doing this in my office where I have a better setup, and the department chair and dean are backing that. If professors in other departments are saying or doing different things, you're just going to have to go along with that. But the physics department policy is that lecture classes will not meet in person. Now, at the moment, some of the upper division labs, or really any labs above the 1,000 level, some of the labs, including yours, will be meeting in person. And the reason for that is that, first of all, using the equipment is part of the point. And second, whereas in the freshman labs, you might have 30 different people touching the same piece of equipment during the week. In your labs, you're only going to have 1 or 2 or 3 people maybe 4 touching the equipment. And between experiments, we can wipe them down. You can bring sanitary wipes or hand sanitizer or whatever and wipe down anything that you're touching. So with fewer people touching things, it's a much less risky situation. That said, it's always possible that the lab will be canceled. If the lab is canceled, then what you'll probably do for the rest of the semester is watch videos of the experiment and then receive data that someone else took and write a report analyzing that data. It's decidedly suboptimal, but so is everything else about this situation. As far as how things are going to run in class, I'm going to be posting and discussing lecture notes. You might be wondering, why didn't I ever post my lecture notes before? The short version is that notes that you use to speak from are very, very different from notes that you give other people to read from. So I will be providing these notes as well as I can. You can always come to campus for the Wi-Fi if your home Wi-Fi isn't working well for this. We don't mind if you're on campus. We just don't want to pack 30 of you into a room. If those of you who need to come are a smaller percentage and you're spread throughout the campus into quiet corners, that's not nearly the same kind of risk. The readings are still the same. They're always available. They're posted in the syllabus. And ultimately, for any physics class, the homework questions are really telling you what it is that you should be studying. So however well this lecture or a regular lecture or whatever works or doesn't work, the homework is what you should be studying. Related to the homework, I have redone it so that the assignments due in the next couple weeks are not posted just as files, but they're posted as assignments in Blackboard. And the difference for Blackboard is that assignments are underlined and they're placed at the bottom of the page. That wasn't my idea, that was theirs. But if you click on it, then just like with the midterm on Friday, you will see a place where you can attach files. So just upload scans. One other thing I should say about this is that you will be able to ask me questions. I've had all of you mute your microphones because if we have 30 microphones going at once, everything is going to get very noisy. We're going to hear everyone static. But there should be a button that you can click to raise your hand. Could someone try raising their hand? Okay, Ben did it. Now, Ben, what I'm going to do is I'm going to try to briefly share your screen, if you don't mind. Wait, what was I going? No, that was the wrong thing. Okay. I want to unmute. Ben, I want to try to share your screen. I'm going to try to make your screen visible to everyone so that you can point out where the raise hand icon is, because I don't see it on my screen. Is that okay? Let's see if I can share his screen. All right, I am trying to share Ben's screen. All right, let's see. No, I am not seeing Ben's screen. Ben, could you just say where you found the raise hand icon? I can't hear you.
Can you hear me now?
I can hear you now. Where's the raise hand icon on the screen?
Well, at first you were full screen, but then I unfull screened you, and on the right side there's a list of students for me as well, just who's participating in the call, and then at the bottom right hand of that is a button that says raise hand.
Okay. All right. Good to know.
Yeah.
Then I'm gonna mute you. It looks like, all right, you muted yourself. Good. And finally, lest you think that everything has changed, nothing can stop me from talking about books. So I want to highlight one of my favorite biophysics authors, Philip Nelson at University of Pennsylvania, has written several books on biophysics, and His most classic one is really for grad students, but this book, From Photon to Neuron, is interesting in that it combines optics from the very beginning with quite a bit of the biophysics needed to understand what happens inside a neuron when a signal is received, when light hits it and a cascade of chemical reactions sends a message to the brain. It's a rather unique book. It's at a level that you're ready for. And it really goes from very, very purely physics stuff in optics to very, very biological stuff. And so if you're kind of curious about the interface between optics and biology, and you're looking for something that can take you on that road, starting from where you're at as a physicist and taking you to where someone who's more interested in biological applications would be, this is actually an excellent book for it. And I'm going to continue plugging books. But let's get started with physics. So we've been talking for a couple weeks about what happens when light behaves as a ray, when we just ignore the fact that light is actually a wave and just talk about light as something that travels in straight lines. And that's a very useful approximation. It's an approximation that enables us to understand and build the lenses and mirrors that are used to manipulate light and make most of our technologies with light possible. But it's not everything with light. And so we're going to go back into the wave nature of light. Now, we derived the wave nature of light from Maxwell's equations. But that's not how this was originally done. How this was originally done was through some experiments that actually came before Maxwell's equations, before they knew what type of wave it was, before they knew that it was a wave of electric and magnetic fields that push and pull on charges. They knew it was a wave of something. And one of the experiments was Poisson's spot. We can debate whether this was actually the decisive experiment. The historians of science are the ones to decide that, because they'd have to go back and read what people thought at the time. Were people at the time actually persuaded by it? But it should be persuasive to us. In 1818, there was a contest to see who could come up with the best article on the theory of light. And Poisson, who was judging it, looked at the wave theory and said, no, wait, this is absurd, because if this theory is true, then in the shadow of a circular object, you're going to have a little bright spot in the middle. And we'll get to why that is. And so someone else named Arago did the experiment, and he found the bright spot. And it's kind of ironic that the guy who thought the whole thing was BS is the one who got his name on it, even though he neither did the experiment nor did the theory. And some books now call it Arago's spot. And then it turns out that some Italian scientists 100 years before that had actually done the experiment but didn't fully understand what they're looking at. Here's the idea of Poisson's spot. Take some light and shine it on a circular object, like a little ball bearing. Well, it casts a shadow. And if we look at that shadow, we see mostly dark. And then we see rings going out around the edge of the shadow. And those rings are due to interference effects that we'll get to in a week or so. But right at the center of it is a bright spot. And we actually have a really good demo of it in the department, which I can't show you for obvious reasons. And here's why it happens. It happens because light spreads out. If light just went in straight lines, then we would ignore all these paths here from it. We'd see some light going here straight, some light going down there straight, and nothing going in between. But in fact, light spreads out at the edges of an obstacle. And you're actually familiar with waves spreading out at the edges of an obstacle. If someone is standing with their back to you and they talk, the sound waves don't just go straight in front of them, moving forward. If they did, you wouldn't hear anyone standing with their back to you. Instead, those waves, which have a wavelength much longer than the size of their mouth, those waves spread out in all directions. They even spread out in backwards directions, like little ripples on a pond. And that's how it is that even though they're standing with their back towards you, the sound started off traveling away from you. it very quickly spreads in all directions. Now, these spreading effects are only noticeable when the wavelength is large compared to the objects we're looking at. But that's why we mostly see shadow. But let's look carefully at the center. The center of this thing is equidistant from every point on the edge of the circle. And because it's equidistant from every point on the edge of the circle, every path that light could take from the edge of the circle to here takes the same amount of time. So all the waves arrive at the same point in their cycle, which means they add up constructively, like we discussed with waves before, earlier in the semester. So if they add up constructively, we must get some pretty bright light here. But if we go off center, now different paths take different amounts of time. And so at most points on the screen, you're going to have either perfect cancellation or very close to perfect cancellation. If you look again at the experiment, you'll notice that around there's the bright spot, and then you can see little ripples around the edges of the bright spot, but they get faint very, very quickly. And the fact that they get faint very, very quickly is why we normally just notice shadows. So the two key things from this experiment are that light actually does spread out. You might need to use a pretty small object to see the effects, because the smaller the object, the closer it is to the wavelength. And when it spreads out, it interferes like an oscillating wave. If anyone has a question at this point, raise your hand and I'll unmute your mic. Anyone? Anyone? Bueller? Bueller? Viruses will not stop me from telling lame jokes about 80s movies. Okay. That was one experiment. Another experiment that was also pretty important that we can analyze a little more quantitatively. Poisson spot can also be done quantitatively, but the math is harder. One where it's easier to analyze things quantitatively is to look at two slits separated by a distance d. And when light passes through those two slits, what we see is that instead of getting a shadow here and a shadow here, there's also a bright spot in the middle. And furthermore, within each of those bright spots, there are actually sub-bright spots. We're getting ripples here, okay? We're getting something that doesn't look at all like just two shadows, maybe two shadows smeared out a little bit because, you know, the light rays coming in weren't perfectly parallel. We get something that can only be understood in terms of interference. And so at this point, we need to start doing some diagrams and math. And for that, I'm going to switch to handwritten notes. So let's start by thinking about what would happen if we only had one slit. Well, if the slit is very tiny, then we could treat it as a point source of light. And we know that the field of a point source is just e to the IKR over r. So the intensity is going to be 1 over r squared, or proportional to 1 over r squared. There's a whole bunch of constants in here. But we're going to mostly just talk about where are the peaks, where are the troughs, and how do things get brighter or dimmer, because those are the things that are easy to measure in experiments. All right, so the field is proportional to e to the IKR over r. The intensity is 1 over r squared. So you would just see a bright spot here that slowly decays. Now, the key assumption is that the width of that slit is much smaller than the wavelength. All right, that way the path from the top of the slit to your detector and the path from the bottom of the slit to your detector take, if not exactly the same amount of distance, in the same amount of time, at least very, very close to the same time. All right? So that there's no chance of these interfering destructively. They're all just in phase. So it would be like taking this and this e to the IKR over r and multiplying by 2. By the way, can you guys see my mouse on here? Can someone unmute themselves and tell me if you see the mouse moving around? Anyone?
We see the mouse.
Okay, good. Good. All right, now if we've got two slits, all right, even though technically the slit is finite, there are many paths from within this slit to there. We'll just treat them as one path because they're all essentially the same. The two slits are separated by a distance d. So these two path lengths are different. So we're adding two waves. And we're going to assume that I've left out the direction of these two vectors. We're just assuming they point in the same direction. So the electric field is proportional to e to the ikr1 over r1 plus e to the ikr2 over r2. And we want to work with this and figure out how the intensity depends on r1, r2, the slit spacing, and theta. So intensity is 1/2 some constants multiplied by E star E, which is proportional to 1/2 all of this. We've got the complex conjugate, e to the minus ikr1 over r1 plus e to the minus ikr2 over r2 multiplied by the field. We're going to keep that 1/2. It's convenient later. It cancels out some things. And when we multiply these two expressions, we get 4 terms. Now, 2 of them are easy because if I multiply this by this, I'm taking this times its complex conjugate. And likewise, if I multiply this by this, I'm getting this times its complex conjugate. So I get 1 over r1 squared and 1 over r2 squared. So those two terms are easy. If I multiply this by this, or this by this, I'm going to get e to the ik either r2 minus r1 or r1 minus r2. And so those two things, I've got two exponentials where the exponents are just the negative of each other. And we know that when we add two exponentials that are just the negative, where the exponents are just the negative of each other, we get 2 times the cosine of that exponent, assuming the exponent is imaginary. All right, so this is what we get. Now, we're going to make an approximation. We're going to say that R1 is roughly R2, so that their difference is small. Maybe their difference is 10 to the minus 7 meters or 10 to the minus 6 meters. So a few hundred nanometers to a few microns. And we're going to assume that R1 and R2 are at least 10 centimeters or 10 to the minus 1 meters. That's a pretty good assumption. So if we plug in numbers, then what we find is that 1 over R1 squared would be 100 inverse meters squared. And 1 over R2 squared would be 99.999 inverse meters squared. And 1 over R1, R2 would be very close to that. So to many decimal places, we could treat these 3 terms like they're the same. And then we just get that our intensity is 1 over R squared, is 1 plus 1 plus 2 cosine k delta R. And then divide by 2, and we're left with 1 plus cosine of k delta R. Questions? Anyone? This is all as clear as brand new expensive optical glass sold by my buddies in the Optical Society, really? Just because I'm not standing in front of you doesn't mean I can't sit here with my arms folded and make it awkward until someone asks a question. No questions? Okay. So let's figure out where the intensity is a maximum. Well, we got 1 plus cosine k delta R. If that cosine is 1, then we're writing 1 plus 1, that's 2. That's going to be true when k delta R is 2 pi times an integer, or 2 pi over lambda times delta R is 2 pi times an integer, or delta R is lambda times an integer. And that just means that the two paths are in sync with each other, even though they differ by a full wavelength. Let's say that I've set this up so that they both start at their peak and end at their peak. but one of them goes through 2 cycles getting there, and one of them goes through 1, 2, 3 cycles getting there. Well, they both arrive at their peak, they interfere constructively. Conversely, if the intensity is a minimum, even 0, then cosine of k delta r is -1. So k delta r, or 2 pi delta r over lambda, could be pi, or 3 pi, or 5 pi, etc., or pi times 1 plus 2 times an integer. So if we do the algebra, we're going to get that 2 delta r is the wavelength times 1 plus 2 times an integer, or delta r is the wavelength times 1/2 plus an integer. So the waves are 1/2 of a cycle out of sync. One of them's at its peak and the other one's at its trough, and they cancel out. Also, and here's the important thing, not only do we get those oscillating ripple effects up and down, which is what we saw in the experiments or in the photos of the experiments, but at the center of the screen, that is equidistant from the top slit and the bottom slit. So we're going to get constructive interference there. And if we get constructive interference there, well, that also matches what we saw in this experiment and also in Poisson's spot. Again, even though they are slightly different situations, they have the same qualitative idea that at the center, where you would expect to see a shadow, you get constructive interference. And these are results that you just cannot hand wave away with the wave theory, with the particle theory of light. You need a wave theory for this. And so we've got a calculation that matches one of the more important experiments in the history of optics. And we also have a formula that we can use to figure out where exactly are all of these peaks, where exactly are all of these troughs. In principle, we could also figure out halfway points. We could predict that, all right, it's half, if it's max intensity here, and it's 25% there, and it's 75% there. But in practice, we don't spend a lot of time on that. Even in more advanced optics, yes, people do learn how to calculate those field profiles. They do matter. But what matters most is just knowing where the bright spots are and the dim spots, or the zeros, when it's perfectly destructive interference, because those are the things that are the easiest to identify in the data. All of the fine points in between, you have to have a very good measurement. And while people want good measurements, those who are good at measurements know that good measurements are few and far between. They should never be taken uncritically. But the peaks and the troughs are much easier to find. So we're going to focus on those for very practical reasons, not just because the math is easier, but because they match up with what people do in the real world. Now, let's consider what happens when the spacing between the slits and the detector is very large. So L here is very large compared with D. Then these two paths are almost parallel. They may not look that much almost parallel on this drawing, but that's because none of this is to scale. But if they're very close to parallel, then this line here between them will be perpendicular to the bottom path and perpendicular to the top path. And so if this angle is theta, then this angle here is 90 minus theta, because these two have to add up to 90. So you've got 90 minus theta, and all of this is a right triangle here. So we got 90 minus theta plus 90 is 180 minus theta. So this angle has to be theta. And then this path difference is opposite to theta. So that path difference is going to be d sine theta. All right. So then again, for constructive interference, d sine theta is an integer multiple of the wavelength. And for destructive, d sine theta will be a half integer, or a half plus an integer times the wavelength. And then furthermore, when people are trying to predict things in experiments or do some of the calculations on the homework, oftentimes if this is a really large distance, then Y will wind up being much smaller than L. So sine theta is roughly tan theta. This is only true for small angles. You should not assume this in all cases. But if L is very large, then sine theta is roughly tan theta, and tan theta is Y over L. Y over L here. All right? Then you may be thinking, well, wait, shouldn't tan theta be a larger distance over L? But keep in mind that everything is much larger than D, so this little gap here is inconsequential. All right, so we put all this together, and we get that our intensity is proportional to 1 plus cosine of kd sine theta. Now, as soon as I write out a function like this, people start interpreting it in all sorts of interesting ways. They start thinking, oh, maybe that's cosine of kd theta, or kd cosine of theta, or kd sine theta times cosine theta. They try to take this expression here and turn it into literally anything else before running it through their calculator. I'm sorry, but it's this. You have to first compute sine theta, then you have to multiply by kd, and then you have to take the cosine of all of that. Any questions? This feels a lot more rushed because I'm not pausing for you guys to write. I'm not improvising on the board. So we're going to get through this quickly. Okay, now one question we could ask, what if D is very tiny? Well, then kd sine theta is always less than D. And if D is much smaller than the wavelength, then d over lambda is much less than 1. 2 pi d over lambda, which is kd, is much less than 2 pi. So we're going to be taking something way less than 2 pi, multiplying it by sine theta less than 1, and plugging all of that into a cosine. Now, if we plug a very tiny number into a cosine, what are we going to get when we take that cosine? Anyone? Unmute yourself.
1?
Yeah, we're going to get something very, very close to 1. Okay, so if we've got a very tiny number, if we got a very small particle, then we're not going to see any of these effects. Now, I'm harping on this because the world has plenty of small particles that are easy to find, molecules of gas. They don't produce these kinds of effects. The world has plenty of large objects. They don't really produce these effects. So our ancestors weren't able to figure this out. There is a reason why the Greeks and the Arabs did not figure this out. And that's because these experiments require objects that are about as small as people can reliably make and manufacture. And it wasn't until the Industrial Revolution that they did these experiments. It wasn't until people were accustomed to not just making small objects on a craft basis, handmade one by one, but making things very small and reliably so. You know, mass scale manufacturing of pins and needles and other things like that. Mass scale manufacturing of gears for mechanical watches. It wasn't until then that they could do experiments where you need to have reliable measurement of an object that's a millimeter or smaller in order to see these effects. That's why modern physics happened when it did, because once they could reliably do measurements of objects a millimeter, maybe even a little bit smaller, then they could get noticeable interference effects with light. Then they could discover the wave nature of light. And once they discovered the wave nature of light, then very quickly they would discover emission spectra from atoms. They would discover that atoms emit certain specific wavelengths of light rather than just emitting a broad rainbow of colors. And once they discovered that, they could figure out the nature of atoms. And once they discovered that, they could get quantum mechanics, they could get nuclear physics, they could get electron microscopes, transistors, lasers, the internet. So all of this happened because of the Industrial Revolution. Scientists like to say that we created industry and engineering. Well, we certainly contributed to those things. But at the same time, science has benefited at least as much from engineering as engineering has benefited from science. Modern science, the modern philosophy of science is a whole separate thing. Our modern understanding of the universe comes from precision measurement and manufacturing and comes at least as much from engineering. All right, now what I'm going to do is I'm going to switch to Mathematica. And I've got a notebook that just calculates that intensity. It calculates 1 plus cosine of KD sine theta. And we're going to say that the wavelength is 0.5 microns, and that the the K is 2 pi over that wavelength. And then we're just going to graph that intensity. And we're going to graph it as a function of theta. And I get to decide what D will be. And I get to decide what the maximum angle will be. So let's make D really small. Let's make D like 0.05 microns or 50 nanometers. What you see here is that 1 plus cosine of KD sine theta is almost the same everywhere around here, because no matter what value of theta we plug in, anything from minus 90 to plus 90, once we multiply that by KD, and let's just see what K times D is. K times, once we multiply that by 0.6, we're taking the cosine of something that's always pretty small. Maybe we see a faint ripple. We get some idea that there's some kind of structure we're diffracting off of, but we can't see any details. If I make D equal to the wavelength, well then out here at an angle of 30 degrees, because D is 0.5 and lambda up there was 0.5. At an angle of 30 degrees, we see something. And let me see if I can do this by hand. Now I have to switch devices. So hang on. I'm going to switch to a tablet that I can write on. So I have to first go into Zoom and share my screen, and then switch to this. Do you see Mathematica, or do you see something where I'm scribbling? Which do you see? Do you see scribbling or Mathematica?
Neither.
What do you see?
Nothing. Just your previous notes.
You're still sharing your notes, so I think you have to share that first and then share your.
Oh.
Yeah.
Okay.
I wasn't sure if we were supposed to see that.
There we go.
Okay. All right. Sorry. I thought it was sharing my screen, but no, it's sharing a program. Okay. Sorry. I'm new to Zoom. All right. So I've been having, my bad. All right, let's start over. We got this Mathematica file up here, which is, by the way, also available in Blackboard. Let me see if I can share Blackboard. All right. So what we see in Blackboard, let me go to course documents, Mathematica simulations. All right, here's a Mathematica file that I'm sharing today. And I think that a while back, I posted something in here about how to get Mathematica. Yeah, get Mathematica for your own computer under announcements. All right, so if you look at the January 31st announcement on Blackboard, there are instructions for getting Mathematica. But now I'm going to go back to sharing my Mathematica screen. Okay, so first I define a function that calculates the intensity. And then we're going to say that the wavelength is 0.5. And then I've got something that I can play with. All right, I can make the slit spacing D be whatever I want it to be. And I can plot it from 0 to a very small angle if I want to look at fine details. Or I can plot it from 0 to 90 or 0 to minus 90 if I want to look at large scale features. And we can play with the slit spacing. And we can see that when we have very few, very narrow spacing between slits, we don't get much of a pattern. We have a peak, we have one interference minimum, and then by 90 degrees, it's just kind of petered out. If I make the spacing between slits very large, then we see a whole lot of peaks. We see something that might look more like that experiment I showed you before. And the reason is that here it helps if I switch to, let's see if I can switch to my tablet. If I'm able to switch to my tablet. Are you seeing my tablet yet where I'm scribbling? Probably not. Let's go back into Zoom. Let's do a share. All right, I'm sharing my screen. And now I'm switching. Okay, someone tell me what you see at this point. Mathematica or scribbling?
Still seeing Mathematica.
What?
Still seeing Mathematica.
I see the scribbling, but you have to go to view options and click the other Alex Small, and then you can see the scribbling.
Okay, I see. So my tablet is the other Alex Small. And
The view options thing's at the top of the bar.
okay. Yeah, let's see. Am I able to make my other, you see, the other me is a co-host, but for some reason I cannot get my co-host. I start doing a share. So I go into, oh, maybe he has to claim host. Okay. So the other me has claimed host, and he is going to share his screen. Why am I talking about myself in the third person when I'm using two accounts? Okay, do people see the scribbling now? Does anybody not see the scribbling? All right, I'm taking that as we're all good. So the condition was that we get destructive interference if KD sine theta equals 2 pi times m plus 1/2, or d sine theta equals m plus 1/2 lambda. So we get destructive interference when sine theta equals m plus 1/2 times lambda over d. Now, eventually, if we make m really large, we're going to have that sine theta is greater than 1. This condition can't be satisfied at all angles. But if lambda over d is really tiny, let's say that lambda over d equals 0.1, well, then we could have that sine theta is equal to 0.1 times 0.5, or go away, what happened? Or 0.1 times 1.5, or I keep tapping the wrong thing, or 0.1 times 2.5, etc. So we can have a whole lot of interference minima, all right? And that goes to, let me see if I can go back to sharing Mathematica. Okay. Did you guys hear any of what I just said, or when I claimed host, did I shut off the other mic?
I heard it.
I heard it.
Okay. Do you see Mathematica now?
Yeah.
All right. You might need to, for those who, if you don't, then just try switching screen view like you did before. So what I was trying to take away is that you get a interference minima when sine theta, I can do that notation quick, equals m plus 0.5 times lambda over d. So for large d, we get a whole lot of these. For small d, we get few of these. So what that means is that for large d, well, we get so many of these that you won't resolve any structure. It's just a blur. And for very small d, like a molecule, everything just looks flat. So it's only in that intermediate regime that you get peaks that are far enough to be resolvable, like this, but not so far apart that there's only one like that. And it was necessary to hit that sweet spot. That's what the Industrial Revolution enabled. So I'm going to switch back to my handwritten notes. All right, another thing we could talk about is what would we do if we had more than two slits? Well, we would just do the same addition that we had before. The electric field would still be from each slit, e to the IKR over R. We'd be adding up instead of 2, maybe 3, maybe more. It would just be a summation over slits. That's a messy summation, but it's supposed to be the sum from j equals 1 to however many slits you have, e to the IK RJ over R. And you might ask, why is the denominator not RJ? It's because all the paths are exactly the same, or almost exactly the same. And you'll do some of that in the homework. All right, this kind of goes over some of what I was saying before. The second point is that the angles for the peaks and troughs are very small for macroscopic objects. There's actually another problem, which is that sunlight was no good for this. The sun, if you look at it in the sky at sunset, when you can safely look at it, the sun is not a point object. It has finite size, which means there's light coming from one edge of the sun and light coming from the other edge of the sun. So they're coming in at different angles, all right? And its angular size in the sky is about ½ a degree. And so the difference between these two paths will be d sine theta, or d sine of 0.5 degrees. And you will need to have that d sine theta is less than the wavelength, much less than the wavelength, in order for any of this to work. And that means that d will have to be much less than 5 times 10 to the minus 5 meters. And you'll go over some effects related to this on the homework. But that's one more reason why the Sumerians, the Greeks, and even the Arabs were unable to do this. All right, one final thing, and then we're actually going to, amazingly enough, break at 10:50. A key experiment, which we're going to go into on Wednesday, is Newton's rings. So what Newton did was he took two spheres, like two lenses, and pressed them against each other. And when you do that, you press either two lenses against each other or one lens against a flat surface, you get very small gaps between the surfaces near the center. So if you look at them with white light, you see constructive and destructive interference of different colors at different points because the gap is different at different points. And if the gap is a wavelength or a half wavelength or 1.5 wavelengths or 2.5 wavelengths, you're going to get different effects. And Newton actually spent, this is what happens if you do it with just a single color from a laser. So Newton spent a lot of time thinking about these experiments. And a lot of people like to say that Newton didn't understand these. Of course, he didn't understand them perfectly, but they like to claim that what held back science was that Newton tried to understand these effects in terms of a particle theory of light. If you actually read Newton's book Optics, he was quite aware that light was not a simple particle, that light had some oscillating behavior to it, just like a wave. I mean, he did this experiment. He saw that there were alternating effects depending on the gap size. What Newton didn't get was that this was because he got the oscillating part of light. He knew that whatever light was, it was oscillating. He thought it was a particle with a property that oscillates. What he didn't get was the spreading of light. And this experiment doesn't really illustrate the spreading of light. So some people have blamed Newton for a lack of progress in optics in the 18th century. Maybe they're right to blame him, maybe they're wrong, but they mischaracterized him when they said that he didn't get any of the wave theory of light. He got the light oscillated. He just didn't get the spread. All right, so we'll talk more about what that comes from and what that leads to on Wednesday. Remember to upload today's homework, upload a scan or photo of it. Whenever possible, upload PDFs or a single file. Does anyone have any questions on anything? On the physics of this, on the policies of the class, on what we're going to do about the crisis, about anything? Okay then, I'm going to shut this off. I'm going to upload it to YouTube, and I will be available in office hours. You can either call me or email me. You can email me anytime, but I promise to respond quickly during office hours. You can call me. Again, you can call anytime, but I promise to be by my phone during office hours. We can video chat. I can set up another Zoom for an individual if needed. But have a good day, and I hope to see you eventually.